Welcome back. This is C253C Microprocessors and Microcontrollers, and this will be lecture 19. Today we will be discussing about the AVR time delays. Previously we discussed about the delay subroutine, how delay subroutine is used to incorporate delays between various instructions in the AVR programs. Today we will be discussing about about how to calculate the exact amount of delay incorporated by a subroutine. And also we will be discussing a very important concept that's related to the time delays, that's known as instruction pipelining. The time delay in any subroutine, it actually depends upon three factors. Three factors. The first thing is number of instructions. In the subroutine. Naturally, more the number of instruction in the subroutine, more will be the amount of delay created by that subroutine. The second thing that it depends upon is the number of cycles taken by each instruction to execute. How many cycles of the crystal frequency, or how we call them machine cycles, how many machine cycles does each instruction take to execute? Most of the instructions in the AVR, in the modern AVR microcontrollers, they only take single cycle to execute. Most of the instructions, 90% of the instructions, but there are some instructions that may take more than one cycle, that may take 2, 3 or 4 cycles to execute. So three factors that determine the exact time delay. The number one is the number of instruction in the subroutine. Number two, number of cycles taken by each instruction in that subroutine to execute. And this will actually depend on the architectural design and IC technology used by a particular microcontroller. Modern microcontrollers, as I have said, most of the instruction in modern microcontrollers, in modern AVR microcontrollers, they only take one cycle to execute. And then the third factor is how long this machine cycle will be. If I say that a particular instruction takes one cycle to execute, will this cycle be of constant duration in every microcontroller? No, of course not. The duration of this cycle, what we call machine cycle, actually depends on the crystal frequency connected to that particular microcontroller, the crystal oscillator. The frequency of the crystal oscillator frequency. That means even if we have a same microcontroller at mega 328, each instruction may take different times if we attach different crystal frequencies to this microcontroller. Same instruction will take different amounts of times to execute, and that will depend upon the crystal oscillator frequency that we have connected externally to that microcontroller. You should remember that each microcontroller needs a crystal oscillator to be connected to this external to particular pins of the microcontroller, and that's used for timing signals, and then that actually decides the width of the duration, or the duration of the machine cycle, and thus decides the amount of time taken by each instruction to execute. So there are three factors: number of instructions, and number of cycles taken by each instruction, and how long this cycle will be, the duration, the time period of this cycle. Now, as I have said, most of the modern AVR microcontrollers, most of the instructions in their modern AVR microcontrollers, they only take one cycle to execute. 1 cycle instructions. That was not case in earlier microcontrollers like 8085. How has this been realized? There have been some changes in the architectural design of the microprocessors in the last decade or so that has actually made this able that most of the instructions are executed in one machine cycle. One of them is the Harvard architecture, because those of you who have gone through your assignments, you may be knowing that in Harvard architecture we have different code memory and data memory, two different buses, so we can simultaneously fetch data and code from the memories. So that makes our microcontrollers fast. Number one thing. Also, if we use RISC architecture, we know that in RISC architecture we have fixed size instructions, and they help us to quickly execute those instructions. And also the third thing that's very important that actually makes this possible, that most of the instructions are executed in one cycle only, is the use of pipelining. What exactly is pipelining? Actually, the execution of an instruction can be broken into many steps, or simply it can be broken into two simple steps. The first step can be fetch, that we have to fetch the instruction from the memory inside the processor. The second step can be execution. Execution can further be divided in three more steps, maybe reading of operands, because first we have to read the operands on which we have to operate, and then we have to execute this instruction, process this instruction, and the third thing may be write back, that we get a result. Maybe the instruction was add, so we fetch two operands, added them here, and then we have to write back the result. So what is the idea of pipelining? What happens in pipelining? The idea of pipelining in its simplest form can be explained as a CPU is allowed to fetch and execute at the same time. That means an instruction is fetched while the previous instruction is being executed. The next instruction is fetched while the previous instruction is being executed. And this idea of pipelining, it can be used to speed up the execution of the instructions. For example, if we have a program, I may write a program here, instruction 1, instruction 2, instruction 3, instruction 4. We have 4 different instructions in our program. So in a non-pipelining system, what will happen? If this is my time t, instruction 1, first of all, instruction 1 will be fetched, maybe in a finite time. I will call it fetch 1. Maybe in t seconds. T can be very small, it can be micro millisecond, t seconds, and then this instruction will be executed. I will call it execute 1. The first instruction will be executed. Maybe again it will take t seconds or t microseconds. Doesn't matter, t can be very small, 0.0000 seconds, that's t microseconds. And after that, next instruction will be executed. Fetch 2, it will also take t seconds maybe, and then we have execute 2, it may also take t microseconds. Similarly, we have 2 other instructions. We may have fetch 3, execute 3, fetch 4, execute 4, and all of them may take t seconds. So each instruction is actually taking 2 t seconds to fetch and execute. Then the next instruction is also taking 2 t seconds. That means for these 4 instructions, the total time taken by the processor to execute all these 4 instructions was actually 4 into 2t, that means 8t seconds. This is the non-pipelining system. Non-pipeline. In pipelining, what is the idea? We can overlap these steps. When the first instruction has been fetched, it's being executed. When it is being executed, we can start fetching the second instruction. We can have something like this. Fetch 1, and then it will take t seconds, of course. Then in the next t seconds we are doing execution of this first instruction, but at the same time, since we have a separate code memory, we are fetching the next instruction. Fetch 2, and in the third time interval, in third t seconds, what we are doing, we are now executing this instruction 2, or I can make it like this. Execute this 2. At the same time, I will fetch the third instruction. And in the next t seconds, what will happen? I will execute this third instruction, and also at the same time fetch fourth instruction. And in the next t seconds, I will execute this fourth instruction. So what happened here? Previously, for these 4 instructions, it took processor 80 seconds to execute, but here it only has taken it 5t pipelining system. 5t seconds. That means for 4 instructions, only 4 plus 1 t seconds. We have saved 3 time units, 3 machine cycles, 3 units of time we have saved. And if the instruction number of instruction is very large, maybe number of instruction is 1000, what will happen? This system will take maybe 2000 cycles or 2000 t seconds to execute, but this system, pipelining system, will only take 1000 plus 1. The first one is extra because in the first phase we are only fetching the instruction. We can't execute the previous instruction because it's the first instruction. 1000 plus 1 cycles to execute. That means we have almost saved half the time period. This is pipelining. But there's a one small limitation that happens in the pipelining. What is that? The limitation is that in pipelining, the speed of the execution will be limited to the slowest stage of the pipeline. Since there are 2 stages, fetch state and execute stage, whichever one is the slowest, we have assumed that they are equal, t seconds for fetch, t seconds for execute, but maybe they are not equal. This takes one of them takes less time than the other. What will happen? The speed of execution will be limited by the slower stage. That's a small limitation of the pipelining. So pipelining actually helps us to save the time of the execution, and it actually helps us that each instruction, most of these instructions will be executed in a single machine cycle. Now there is one more thing. the problem with the pipelining. And that's not exactly a problem, but sometimes we cannot implement the pipelining, and that is known as branch penalty. Again, let me give an example. This time maybe a real life, real program example. We have a program. For example, I'm writing a subroutine. I have a small subroutine. I have used the subroutine in my main program. Here I am only discussing the subroutine. LDI R20 0 cross FF. I'm using R20 as my counter. Then I'm writing maybe a no operation statement, NOP. Then I'm decrementing this R20 and branch if not equal to 0 BRNE to ABC. If it's not 0, if it has not reached 0 yet, I will go back to ABC and again execute these instructions, and if it has reached 0, I will return to the main program. Since we are using pipelining, what will happen when this instruction is fetched? When this instruction is executed, this will be fetched. When this instruction is executed, the next instruction will be fetched. And when this branch instruction is executed, the next instruction will be fetched. But after executing the branch instruction, if R20 has not reached to 0 yet, the processor will come to know that RET was not the next instruction to be executed, but the next instruction to be executed was this NOP, because the program is not sequential here. There's a decision. So what will happen, since the RET will already have been fetched by the processor, it has to flush it out and fetch NOP again. So that means pipelining will not work here. Whenever there is a branch instruction where the control goes out of sequence, pipelining doesn't work there, because in pipeline, again I will repeat, what will happen when this instruction was executed, processor already had fetched this instruction, fine, and when this instruction was fetched, processor already had fetched RET instruction. But when this instruction was executed, it was fully executed, it had already been fetched, the processor came to know that the next instruction to be executed was not RET, but it was this NOP here, because it was R20 was not yet equal to 0, so we had to branch here to ABC. So since RET was already fetched, RET instruction was already fetched, the processor has to flush it out. So it may take extra machine cycle to fetch NOP again. So that means that in case of branch instructions, pipelining doesn't work. Similar is the case if there are maybe 3-4 instructions in my main program, and sometimes I'm calling an instruction and calling a subroutine called delay. So when this instruction was executed, processor had fetched this instruction, and when this instruction was being executed, processor already had fetched the next instruction immediately below the call instruction. But when this instruction was fully executed, it came to know that I have to jump somewhere else, I have to jump to the delay subroutine. So this instruction had to be flushed out, and this instruction had to be fetched again. That means these branch instructions, these calls, these jumps, these conditional branches, or even the return statement, they take extra machine cycles to execute. Most of the other instructions only take one, and this is called branch penalty. The penalty is an extra instruction cycle to fetch the instruction from the target location instead of executing the instruction right below the branch. You should remember that the instruction below the branch has already been fetched and is next to be and was next to be executed. But when this instruction was executed, we came to know that the processor has to branch somewhere else. So as I have told you, that the vast majority of the AVR instructions, they take only one machine cycle, but some instruction may take 2, 3 or 4 machine cycles, and these instructions are jump, call, return, and all the conditional branch instructions like BRNE, BRLO, and so on. For example, LDI instruction, it only takes one machine cycles to execute. Decrement, it also takes one machine cycle to execute. Out, it also takes one machine cycles to execute. Which other instruction we have studied? Add, it also takes one machine cycles to execute. NOP, it also takes one machine cycle to execute. Jump, it takes 3 machine cycles to execute. Call, it takes 4 machine cycles to execute. Return, it also takes 4 machine cycles to execute. Conditional branch, for example BRNE, they may take 2 or 1 machine cycle to execute. If the condition is met, that means it has to branch, then it will take 2 machine cycles to execute. And if the condition is not met, maybe in this case, when finally R20 has reached 0, in that case BRNE ABC, because it will not be jumping to ABC at that time, it will simply execute the next instruction, that is RET. That means RET is it's not needed that RET is being flushed, has to be flushed out of the processor, and NOP instruction, this ABC instruction at ABC is fetched to be executed. In that case, BRNE instruction will take only 1 machine cycle. So conditional branch, they may take 1 or 2 machine cycles to execute. If the system is branching, then it will take 2 machine cycles to execute. If the system is not branching, that's when condition is not met, it will take only 1 machine cycle to execute. Now, as I have said earlier, what is this machine cycle? Actually, it takes a certain amount of time for the CPU to execute in an instruction. That time is referred as machine cycle. Okay, and this will actually depend upon the crystal oscillator along with the on-chip circuitry that we have connected to the AVR microcontroller. In most of the AVR microcontrollers, this instruction cycle or machine cycle is actually equal to the time period of the crystal oscillator. For example, if we have connected a crystal oscillator of 1 megahertz, time period of the crystal oscillator will be equal to the inverse of it, that is 1 microseconds. Okay, that means 1 machine cycles in this case will be equal to 1 microseconds. If the crystal frequency is 10 megahertz, we will have 0.1 microsecond time period of the crystal frequency, and 1 machine cycle in that case will be equal to 0.1 microseconds. Mostly we connect a crystal of 16 megahertz. The crystal 8 or 16 megahertz. The crystal is 16 megahertz. The time period will be 1 by 16 into 10 raised power minus 6 seconds, or 1 by 16 microseconds. That will be equal to 0.0625 microseconds. So our machine cycle is equal to 0.0625 microseconds. Similarly, if the crystal frequency we have connected is 8 megahertz, our machine cycle will be equal to 0.125 microseconds. Now, coming to the exact, so if we have an instruction like, for example, that means now, as I have already said, that the total time taken by an instruction to execute will depend upon the number of machine cycles that instruction takes, and also on the crystal frequency connected. For example, let's assume that we have connected 1 megahertz crystal frequency. That means one machine cycle is equal to 1 microseconds. How much time will LDI instruction take to execute? Since LDI takes one machine cycle to execute, one machine cycle is equal to 1 microseconds. That means LDI will take 1 microsecond to execute. Similarly, decrement is also a one machine cycle instruction. It will also take 1 microsecond to execute. Same is the case with add, out, NOP. What about jump? As I have told you, jump takes 3 microseconds, 3 machine cycles to execute. That means jump will take 3 microseconds. Simple. What about call? Call takes 4 machine cycles, and same is case with return. That means they will take 4 microseconds. This is assuming that there is a 1 megahertz crystal connected to the ATmega 328 microcontroller. What if there is 16 megahertz crystal attached? LDI again will take 1 machine cycle, but this time 1 machine cycle is equal to 0.0625 microseconds, or that comes to 62.5 nanoseconds. 62.5 nanoseconds. What about jump instruction here? Since it takes 3 machine cycles, it will take 3 times 62.5 nanoseconds. That will be equal to 3 parts. 187.5 nanoseconds to execute. So whenever you calculate the time delay or the time taken by each instruction to execute, you should know the frequency of the crystal oscillator connected to that microcontroller, and also the number of machine cycles taken by each instruction to execute. Coming back to the exact time delay calculations of a delay subroutine. For example, our delay subroutine is something like this: delay LDI R20 0 cross FF. I am loading the highest value in R20, that's 255. Then I'm saying NOP couple number of times. Then I'm decrementing this R20 and checking if it has reached to 0, branch. If not equal to 0, if it's not equal to 0, I will branch to NOP. And once it has reached to 0, it won't branch to ABC, but the next instruction will be executed and the next instruction will be returned. This is my subroutine. So how much time this subroutine will exactly take? It will depend on 3 factors. One of them is the crystal frequency. Let's assume the crystal frequency is 10 megahertz. 10 megahertz. So that means each machine cycle is equal to 0.1 microseconds. Fine. And the next thing that it will depend upon how many machine cycles or the instruction cycles each instruction takes to execute. This will take 1. This will take this takes 1. This also takes 1. This takes 1. Decrement takes 1. Branch, if not equal to, may take 1. Will take 2 when it will branch to ABC, and at the last it will take only 1 when it won't branch to ABC. That is when condition is not met. And the return takes 4 machine cycles. Return takes 4 because it has to load values back from the stack into the program counter. That's why call and return take 3 or 4 both of them take 4 machine cycles to execute. So what will be the total time delay? Total time delay will be these instructions, these 1 2 3 4 instructions will run 255 number of times, because we have loaded 255 in LDI. This will run only once, these 250, and this will also run only once. So what will be the total time period? this one plus 255 times the delay of these instructions, and then plus this 4 for this return, because it will only run once. So one machine cycle of this, because it will only run once, and 4 machine cycles, because it takes 4 machine cycles of return, because it will also run only once, but these 4 instructions will run 255 times. So what's the time delay of these 4 instructions? 1 plus 1 plus 1 plus 2. But the 255th time when BR and E will run, it will take only 1 machine cycle. So that one I will subtract here. So this is the total time delay. And what is the duration of each machine cycle? It is 0.1 microseconds. So multiplied by 0.1 microseconds. I hope you got this. This 1 into 0.1 microseconds for this instruction. This 4 into 0.1 microsecond for this instruction. And then since these 4 instructions, they will run 255 number of times. So 255 multiplied by 1 plus 1 plus 1 plus 2. But since the 255th time, this branch BR and E instruction will take only 1 machine cycle. That's why I subtracted 1 machine cycle from the whole calculation. And this will come to, I have already made the calculations, this will be 128.0 microseconds. What if we have to increase the delay? We can use nested loops, as we have discussed earlier. There are many more examples. This example was from your book. There are many examples from on your book also, and maybe we will be discussing a couple of more examples in the Zoom discussions, Zoom classes. That's it for now. Thank you.